The next speaker is Maxim Knyazkov again, with the report vacuum generation for wall climbing robot adaptive contact to surface. Please.
Okay, hello again. I grade to present paper vacuum generation for wall climbing robot adaptive contact to surface. Many modern heading robots are equipped with vacuum grippers for products that differ in various shapes of gripping surface. Mobile robots, in particular robots moving along complex surfaces, as well as surfaces located at different angles to the horizon, carry out fixing on surfaces using vacuum contact devices. If the quality of surfaces is not known in advance, then for the implementation of reliable adhesion, there is a need for automatic recognition of surface properties and adaptation to them. And and here in this figure show a mobile robot with vacuum pressing to the surface based on the operation of a centrifugal pump. The movement of air flows between the robot body and the pressing surface is schematically represented by these arrows. The gap X between the robot body and the motion surface may vary. The vacuum contact device includes a pump and a robot body, the base of which forms an alternating pneumatic resistance with a displacement surface. The flow through with depends on the gap X and absent when X is closer to 0. Another design of the vacuum contact robot involves the use of a turbine. The design of this robot is similar to the design of a robot with a centrifugal pump, with the exception of the vacuum generation device. The movement of air flows between the robot body and the pressing surface is schematically represented by arrows. In contrast to a centrifugal pump, air flows in the case pass through the turbine in direct flow. The full component of the flow velocity inside the vortex chamber can be expressed in the terms of the radial and tangential components. The distribution of tangential velocity is usually expressed as degrees of depends. Consider the relationship between the parameters for the centrifugal pump and turbine. If the turbine power is spent only of creating a vacuum, then the pressure created by the turbine or centrifugal pump can be calculated by this formula. Here, P1 is a section depression. V is the air velocity of the outlet. Rho is the density under suction conditions depending on the gas contact, temperature, pressure, and humidity. The type of pump performance are aerodynamic drag of the contact device. Pressure versus flow rate in relative coordinates are shown in the next figure, A and B. Here, pH and QH and are pressure and flows in the cavities of the pump and the chamber of the vacuum contact devices. Respectively, and PHO and QHO are the average values of pressure and flows in the cavity of the pump and the chamber of vacuum contact devices. Here we finding point A of the operating mood is shown in this figure, where the dependence of the pressure on flow for pump 1 and aerodynamic resistance of the contact devices 2 and 3 and 4 are combining. In this case, graph 2 corresponds to the nominal operating mode, and graph 3, 4 show deviation form from the nominal mode. This point determines the supply of the required amount of air by the injection device into the system and the pressure developed thereby. Thus, the intersection point is the working point of the system under consideration. The inclusion of the pressure feedback corresponds to the adaptive mode of operation when as a result of controlled adaptation. Shadows 3 and 4 come close to shadow 2, and their combination determines the completion of adaptation. According to the result of experiment studies, the effective value of the force of pressing the robot to the displacement surface from the gap X in the range from 0.5 mm to 5 mm was determined. As can be seen from the obtained characteristics, the force F for robots with a centrifugal pump took maximum values with a gap of 0.5 millimeters. In experiments conducted with a turbine-based vacuum generation device, the force F took maximum values when the gap between the robot and the surface was 1 millimeter. To minimize energy consumption, currents in the excitation winding of direct current motors, which drives the structural elements of vacuum generation devices, were investigated. As can be seen from the result obtained in this figure, the lowest energy consumption by a robot with a centrifugal pump corresponds to a gap variation range from 0.5 millimeter to 1 millimeter. The energy consumption for driving the turbine in the second type of robot showed a minimum current value with a gap of 2 millimeters to 5 millimeters. And conclusion. The article presents the result of studies of vacuum devices for contacting mobile robots to a moving surface using a centrifugal pump and turbine. The vortex air motion in such vacuum contact devices and the main parameters are considered. The graphical definition of the operating modes is given, including on the basis of adapting methods. Experimental dependence of the pressing force of the coupling device with the surface on the size of the gap between the contact surface in the phase of movement of the robot are obtained. The characteristic of current strength in the excitation winding of DC motors that drive the structural elements of vacuum generation device, depending on the size of the gap, are analyzed. Many thanks for your attention. Any question?
Thank you. Does anybody has a question? Anybody?
Okay, thank you.
Thank you.